So who's prepared to have a go at helping me with the answer to what the integral of 5x squared dx is?
Would you get 5x to the power of 1 over 1 plus c, and then you cancel out the 1.
That's Taylor, isn't it?
No, it's
No, it's
Nathan.
Nathan. Sorry, Nathan. What you've done, Nathan, is you've taken 1 off the index n instead of adding 1 on.
Oh, right, yeah.
If you look up here,
So,
the top of your fraction is you
oh,
keep
so it
the
should be
a,
to the
which
2
is the
then.
5, yeah, and then you've got x to the 2, so you've got to do x to the 3, 2 plus 1, yeah, and divide by 3.
Yeah.
Yeah, so you're right. You've got to change the index, and you've got to divide by the new index. But if you look at the rule, you've got to add 1 to the index. If you think about differentiator, when you differentiate, you take 1 off the index. That must be the rule to go back the other way. Must be to add 1 to the index, yeah.
And
then plus c on the end is the answer. All right. You always have that constant of integration because you don't have enough information to be able to know what if any constant is on the end of that 5x to the 3 over 3 equation. Yeah.
Okay.
What about B? Anyone else going to have a go at that one? Macca? Go on in, Nathan. You're my lone rider this morning.
2t
2
to the power of 4.
To the power of 4.
Divided by 4.
4.
Plus c.
Plus c. Yeah, and we got a 2 over 4 here, so we can turn that into. We're doing the integral of 2t to the 3 dt, and it equals 2t to the 4 over 4 plus c, and we can turn that into a half t to the 4 plus c. Yep. Okay. Follow that, everyone?
Yep.
If you can't talk with us, just shout up in the chat if you've got a problem with anything, and I'll try and notice it. Right. Okay then. So what we've got on the screen now then is a table of standard integrals. So if we integrate a constant, we end up with ax plus c. It's going to show how that works in terms of the rule you've just been using. If we're integrating a constant
Mark,
a, yeah.
On those last questions, can you just go through
Yeah.
how we check the result by differentiating the answer?
Oh yeah, sorry. Yeah, yes, of course I can. So let me taking the first one, blue. We've got a function. Let's say so. This is the answer. So we got y is equal to 5 over 3 x to the 3, yeah, plus c. When we differentiate, so dy by dx, yeah, we add one. We multiply by 3, don't we? So we end up with 3 times 5 x to the 2 We had 4 there, sorry. No, we didn't, 3. X to the 3. So we bring the 3 down and multiply. Yeah. Take 1 off the index. And all that is over 3. And the 2 3's cancel out. And differentiating the constant, it disappears. So we end up with 5x squared, which is where we started. Yeah. And if we take y is equal to t to the 4 over 2, half t to the 4 plus c. Again, if we differentiate dy by dx is equal to, we bring the 4 down and multiply. Take 1 off the index. Divided by 2. And 4 over 2 is 2 t cubed. And when we differentiate the constant, it disappears. So we're back where we started. Is that cool? Yeah. Good. No dissenting voices. So what I'd want to do is just look at this one. So if we're integrating I with respect to x, let's say, okay, we can write I as I times x to the 0, and that's still equal to a because x to the 0 is 1. Yeah. If we then apply the rules to that, okay, we add 1 to the index, we keep a, we add 1 to the index, divide by the new index. Right, so that is I times x to the 1, and x to the 1 is equal to x. So the answer is ix plus c. So the constant of integration comes back when you integrate a constant. The variable, sorry. When you integrate a constant, the variable of integration comes back with a power of 1. So that's that first one in the table. If we integrate a constant, we end up with that constant times x plus c. Okay. If we do e to the ax, the result is 1 over a. So bring it a out and divide it into 1. Then we keep e to the ax plus c on the end. This special case, 1 over x is ln x. All right. Sine ax goes to minus 1 over a cos ax plus c. And the integral of cos ax goes to 1 over a sine ax plus c. So it's similar to the other table. What you need to do is make sure you know whether you're integrating or differentiating, and making sure you're looking at the right side of your calculus sheet, the integral side or the differential side. Okay, so we'll look at some more examples now. We'll look at we'll look at the formulae, which constant multiplier will help a lot to make this a little bit easier. Okay, so on the bottom of your sheet on integrals, you've got these formulae for integral calculus. So when we have a constant multiplier, I times the function of x, what we can do is immediately take that constant outside the integral and multiply. Yeah. We'll do some examples in a minute, and that is really quite helpful to be able to do that. And then if we have an integral of one function of x added to another function of x, what we do is, first of all, we can take those two constants of those functions outside the integral, but we integrate each of those two functions, f and g, separately and add them together. And then subtraction, if we got one function of multiplied by another function of x, sorry, subtract another function, one function of x away from another function of x. We do a similar thing. We take the two constants outside, but we integrate the two functions f and g separately and subtract the second one from the first one. Okay, so let's have a look at a couple of examples of using those rules. So constant multiplier, when a function is multiplied by a constant, move the constant outside the integral, integrate the remainder, and multiply by the removed constant. So what we can do is, make sure I've got plenty of room. This one, for example, let's say that is equal to 15 times the integral of x to the 5 dx. And then we can integrate, multiply the answer we get by 15. So just get it on my other screen. So we keep the 15 and we put x and add 1 to the index, and we divide by 6 and we add the constant. Yep. We can't simplify 15 over 6 without going into decimals, so we'll leave that as it is. Yeah. Well, we've got this one. We could write that as 3/4 of x cubed. So we can take this 3/4 outside the integral, x to the 3 dx, and that equals, do the integration first, x to the 4 over 4 plus c. We're going to multiply by 3/4. Yep. So it must equal 3 x to the 4 over 16 plus c. All follow that? Good. Right, try those three.
I did 4 with the S thing.
Yeah, integral of, yeah.
Yeah, sorry. And then x to the 3.
X to the 3.
And then
dx, yeah.
dx equals 4x to the 4 over 4 plus c.
4x
Yeah.
to the 4 over 4.
Yeah, plus
C.
c.
Which is, can you see that'll simplify to 4 over 4 is 1 in it. So that's just x to the 4 plus c. Yeah. Other than that, you're right.
Perfect.
Okay. Because these two cancel, yeah?
Yeah.
All right. And then the second one,
I did 4 over 7.
4 over 7.
Or is it the other way around?
Yeah.
What you've got to do here is write this as, so the 7 can come outside, yeah, because like this is like 7 times 1 over x to the 4, yeah. So you can bring the 7 outside, put the integral, and then how have we got to write x to the 4 so we can integrate it? What have you done? What have you done?
What have I done after that?
Yeah. You said you'd end up with 4 over 7. So I don't quite see where that come from.
Oh no, that was at the beginning. That was before that. So the whole thing wrong.
So what we have to do is write this, because this x to the 4 is on the bottom of a fraction. That would be 1 over x to the 4, wouldn't it? We need to write that. You need to get the x to the top of that fraction. So it's just x to the power of something. So what would that be? Using the laws of indices.
How come you don't bring the whole fraction outside like the last question we did?
What whole fraction?
So we had 3x to the power of 3 over 4. Then we brought 3 over 4 outside. How come the 7 only comes outside and the x over 4 stays?
You didn't bring 3 over 4 outside.
On the examples we did before.
Okay, I'll go back to that. These two?
Yeah, so that bottom one there, we brought 3, the fraction on the outside.
Yeah, because that's what you've got as 3/4.
Okay.
This thing here, Macaulay, could just be written like this: 3/4, right? X cubed. So 3/4 is your constant in that case. Yeah.
Yeah.
It's about a matter of different ways you can write things. Yeah. So in this case, we've got 7 with effectively, if I write it in the same kind of notation, we've got 7 over 1 times 1 over x to the 4. You multiply that out, we end up with 7 over x to the 4. It's about getting used to the different ways things can be written and still mean the same thing. Yeah. So all that comes outside is the 7. Yeah. Integral of 1 over x to the 4 dx. But we have to write that as seven times the integral of x to the minus 4 dx. I have to bring that up top of the fraction, remember. Now we can integrate and say the answer is 7 x, 1 on the index, so minus 3, divide by the new index, plus c. Yeah, and the tidiest way to write that is minus 7 over 3x cubed. So bring the x back down, plus c. Okay.
Could you have left it as the one before?
Yeah, you could, if you put it like this, if you were trying to solve a problem, you had that extra information to find c, you'd be able to do it with it in that form. This is just a simplified more succinct form of what's on top.
Okay.
Okay, I'd take that as a valid answer because you've done the integration right. You just haven't simplified it. Okay. This last one first needs to be written as the integral of. So we can take the 3 outside, but we need to write the square root as a power to the half dx. Then we can say the answer is 3x add 1 to a half becomes 3/2 divided by 3/2. Yeah. And what we've effectively got there is, show you this in red, we've got a fraction over 1 on top divided by 3/2. When we divide one fraction into another, we turn the denominator fraction upside down. So what we've effectively got here is 3x to the 3/2 over 1 times 2/3. So the full answer to this is 6. So 3 times 2 is 6. X to the 3/2, yeah, divided by 3. And 6/3 is 2. So the final answer is 2x to the 3/2 plus c, and I'd take that answer. You all follow that? This fraction goes in here up the other way and multiply. So you end up with 6/2 x to the 3/2. You simplify 6/3 is 2. There's your final answer. Right? So you can see the importance of understanding these laws of indices here, because we have to change the square roots into indices form. We have to get a fractional indices up to the top line by changing the sign and so on. Yeah. Okay. So that's the constant multiplier rule, and that's very handy to be able to get that constant out of the way. Right, the sum rule now. So this is the rule where if we've got two functions of x, f, and g, and they're added together, we integrate by integrating each of the functions separately, and we can also use the constant multiplier rule to bring constants outside. Okay, and then if we have subtraction, we two functions of x, one subtracted from the other, we again integrate them separately and do the subtraction afterwards. Okay, so looking at this example here, we've got 4. I'm going to actually put mine on a new page, I think, give me plenty of room. So we're going to integrate 4 plus 3/7 x minus, is that 6x squared? No. Is that 6x squared? Yeah. Dx. Okay. Now, that's equal to the integral of 4 dx plus the integral of 3/7 x dx minus the integral of 6x squared dx, written out in full. Yeah. It's equal to the integral of 4 dx plus 3/7, take the constant outside, the integral of x dx minus 6 integral of x squared dx. Okay, now we can do those integrations. So if we integrate a constant, the variable comes back. So that one's 4x. I'd like to put these in brackets to start with. And then we got 3/7 of x to the 2 over 2, multiply in the middle there, minus 6 x to the 3 over 3. Right? Each of them would have a plus c, but we just put one big plus c on the end there, all the constants added together. We don't know what it is anyway. Okay, and then lastly we can say it is 4x plus 3x squared over 14 minus 2x cubed plus c. 6 over 3, 6 divided by 3 is 2. Okay. Everybody follow that or not, as the case may be. Pity I forgot to start the recording. Oh no, I'll go on anyway. Yeah. Right. Everybody happy with that? Any dissenting voices? Good. So let's have a look at these two. I'll go through these two because they need writing. They're examples of ones that need some manipulation before you can do them. So, taking the first one, we've got the integral of 2x cubed minus 3 all over 4x. What we need to do there is write that differently. We need to write that like this. Integral of 2x cubed over 4x minus 3x over 4x dx. Yeah. And then what we've got in there is some cancelling that can happen. So if I put blue on, that x can go, change that to a 2. Yeah. And this x can go. So we've got an equals, we've simplified it to be, and we've got 2 over 4 here, so that's a half. So we've got x squared over 4. I'm going to write that more as well. It's got a constant, this quarter x squared minus 3/4 dx. Sorry, that's not a quarter, it's a half. 2 over 4 is a half. So that's some simplification up front. So then what we can do is take constants outside. So that equals a half x squared minus 3/4. Keep the integral in there. Dx. And now we can do the integration. So that equals 1/2 times x to the 3 over 3. So we've added 1 to the index and divided by the new index. And then we get 3/4, integrate a constant, variable comes back, plus c. Yeah. Okay. And then we got here, we got 1/2 times 1/3 equals 1/6 x cubed minus 3/4 x plus c. Okay. Any questions? No? Good. Right, the second one, to be able to do this one, so we got b, we got the integral of 1 minus t all squared dx. First thing you need to do here is multiply out these brackets. So if we multiply out 1 times minus t, 1 minus t, sorry, times 1 minus t, what do we get? 1 times 1 is 2. Yeah. Sorry, 1 times 1 is 1. 1 times minus t is minus t. 1 times minus t is another minus t. And then plus t squared. So we end up with this quadratic t squared minus 2t plus 1. All follow that. So over here, we're going to integrate t squared minus 2t plus 1. And then we do the integrals of each of these, and that's dx. Do the integrals of each of these separately. So that's integral of t squared dx minus the integral of 2t dx plus integral of 1 dx. Yep. So it equals t to the 3 over 3 minus 2 t squared plus t plus c. Here's the final answer. So we've got a range of things we have to do at times to get things into a standard ax to the n form. In the case of this, let's multiply out the brackets. there are other ways to do that problem, particularly if the power is higher than 2. Yeah, you can do things another way, but I'm not teaching that yet. I don't know if I have to, but you have to do a substitution. So that's how we can do use the constant multiplier in conjunction with the sum and the subtraction rules. Okay, so let's just have a look at these two with cosines. So A, we've got the integral of 4 cos 3x dx. The first thing we can do is take the constant outside. Yep. Okay. And then the rule here is for a function that is cos ax, the integral is 1 over a sine ax plus c. That's the rule. Yep. So we end up here with 4, the constant we took outside, times 1 over 3 sine 3x plus c equals 4/3 sine 3x plus c. Okay, and then the rule for sine ax is minus 1 over a cos ax. So in the second example, B, we've got the integral of 5 sine 2 theta d theta, different variable, but doesn't matter, still deal with it in the same way. Take the constant outside, integral of sine 2 theta d theta. So therefore, the answer is 5 times minus 1 over 2 cos 2 theta plus c. So it is, final answer, minus 5 over 2 cos 2 theta plus c. Okay, so they're the rules. These two, what I've drawn over here, are the rules for integrating cosine functions from the table. So we use that one, or we use the sine x one there. Okay. So in your handouts, you've got some indefinite integral further practice to have a go at, and you kind of need to work on those so that you get this down to fine art, really, and get used to rearranging these formally. You've got your answers you should get in the square brackets, okay? And I'm here to help if you need me. Either speak up or put something in the chat, and I will help you out. Okay. practice, practice, practice.